Sounds good. All right, thank you, Gene. So I'm Viraj Pandya. I'm an incoming graduate student here at UC Santa Cruz. And I want to tell you about some work that I've been doing for more than 2 years now, primarily with Ryan Bennett and Rachel Somerville, but also with a huge list of collaborators from the Candles and Gamma surveys. Our work is a comprehensive and in-depth look at the thing that many people might consider to be an evolutionary bridge between the blue star-forming population and the red quiescent population. And of course, by that, I'm talking about the Green Valley. So classically, the Green Valley was defined on the basis of uniquely intermediate UV optical colors, using, for example, color mass or colorimetry diagrams as shown here. And the basic idea is that you have this Green Valley population, which is posited to comprise galaxies that are in an evolutionary transitional stage between the blue and red populations. Now, one of the big problems that keeps popping up with the study of the classical Green Valley, especially in studies of low redshift, where the red sequence has already been sufficiently built up and it's already very densely populated in diagrams like this, is when people draw their lines for the Green Valley in many different ways, there's concerns that maybe what they're selecting is actually just a superposition of red and blue galaxies, so what people call a purple valley instead. And it's not clear that whether that purple valley interpretation is what you really are going for when you talk about this transitional stage between the blue and red population. So there are two ways to address this. One way is to go out to high redshift, because we know that the red sequence is not yet sufficiently built up at high redshift, but we know that over cosmic time the red sequence is being built up. And the second way is to use the star-forming main sequence, for which, unlike the previous diagrams, we actually have a physical framework based on equilibrium between gas inflows, gas outflows, star formation, and stellar feedback, that we can use to help explain the tight correlation that we see between the star formation rate and the stellar mass of a star-forming galaxy. And so people now are measuring the intrinsic scatter in the star-forming main sequence as a function of redshift, so we can use those measurements to talk about how galaxies and why galaxies are moving away, below, relative to the star-forming main sequence that you fit. So, for example, you may expect in a statistical sense that if you measure the intrinsic scatter in the star-forming main sequence fit, 95% of star-forming galaxies, for example, might live within 2 sigma of your fit to the main sequence. And so that's kind of what we've done here with the n sigma approach for 7 redshift slices in the Gamma and Candles observations out to redshift 3. So using this n sigma approach, we define this what we call the transition region below the star-forming main sequence. And so we call everything within that transition galaxy, and that things above that are actively forming stars in the main sequence, and things below the transition region we label as quiescent. And so the key question now is, why are the specific star formation rates of quiescent galaxies not as so much more heavily suppressed compared to those of transition galaxies? And before I move on, I do want to just quickly address, what are the 3 possible interpretations for things that actually live in the transition region. You can get star-forming and quiescent galaxies that were scattered into the transition region due to measurement errors in their star formation rates or stellar masses. But assuming that's negligible, whatever remains must be some combination of galaxies that are moving from the main sequence toward quiescence and vice versa on a variety of timescales. And so what we did for the observations enabled by Candles at high redshift is we looked at the structural properties of transition galaxies compared to mass-matched samples of star-forming and quiescent galaxies as a function of redshift, because we know that the star formation histories of galaxies are intimately related to their structural evolutionary histories. So we looked at 3 properties here. The top is the Sir-Sich index, the middle row is the half-light radius, and the bottom row is some measure of galaxy compactness. And what stands out in both the observations, especially the observations, as well as the Santa Cruz semi-analytic model on the right, is a remarkable separation of the transition population relative to the other 2 populations as a function of redshift. And so this result is about 2 years old now, and it's very hard to interpret. There are many possible things that could give rise to this, but there are two main interpretations that are usually considered, hard to disentangle from each other. So the first one is if you assume that the dominant flow of galaxies is from the main sequence toward quiescence, then perhaps morphological change accompanies or even precedes quenching. So you have a main sequence galaxy that is undergoing some kind of quenching event, and it's moving through the transition region, and at the same time it's actually growing a bulge. And in the most extreme cases, you can actually have these events such as compaction, a growth in central stellar density, or a major merger, which then triggers subsequent quenching. The alternative idea, which we've heard about, is the progenitor effect or progenitor bias. And the basic idea there is that at a given redshift slice, the quiescent galaxies in that redshift slice were quenched at an earlier time when all galaxies were smaller. And so, assuming that once a galaxy is quenched, it ceases to grow in size as much as an actively star-forming galaxy, this would, at a given epoch, transitioning quiescent galaxies would naturally be more compact than star-forming galaxies. It's not clear whether this progenitor bias can account for all the trends that we observe, but it likely plays a large role. But we're still working on disentangling the two possible scenarios. It's lots of work required for that. So I want to switch gears here for a second and talk about how galaxies move in the specific star formation rate stellar mass diagram using the Santa Cruz semi-analytic model. So I'm showing a bunch of representative star formation histories here from the SAM. On the y-axis is the specific star formation rate, and on the x-axis is the cosmic age, so redshift 0 is toward the right in each subplot. The blue shaded region in each panel is the star formation main sequence with the ±1 sigma scatter from the SHARC model, completely independent, which Aldo Rodriguez Pueblo talked about. And the green shaded region is the transition region in the SAM as it evolves with redshift. And you'll notice that there is a significant downward, a significant decrease in the normalization of the transition region as you come towards the present day. This is supposed to help account for the fact that a galaxy that you would call quiescent at redshift 2 would probably be considered star-forming, or maybe even a starburst galaxy at redshift 0. So what I'm going to do is I'm going to step through the four main paradigms that we found in the SAM for how galaxies move around in this diagram, and at the end I'll come back and I'll talk about this in the statistical sense. So the first paradigm we have are oscillations on the star-forming main sequence. I've highlighted a few example tracks on here. These oscillations are mainly caused by variations in the gas accretion rate for a galaxy, and they tend to be consistent with the intrinsic scatter of the star-forming main sequence. What's interesting to ask is what fraction of these oscillations actually dip down into the transition region, and so the answer to that is it happens rarely, and when it does happen, it's usually at high redshift. Now, what's intriguing is if these dips into the transition region are accompanied by an increase in the central stellar densities, then these could be intriguing candidates for the so-called green nuggets, the direct progenitors of red nuggets at high redshift. The second paradigm that we call violent quenching. This is very important at high redshift because we do see at redshift 2, redshift 3, we do see many quiescent galaxies that are bulge dominated. And we need some theoretical mechanism to grow a bulge that quickly at early times and to quench a galaxy that quickly at early times. And as far as I understand it, this combination that's been implemented in the Santa Cruz semi-analytic model of major mergers triggering subsequent quasar mode feedback is really the only thing that we have at early times to do this. There might be alternatives, but as far as I know, they do not have not been published or are not known. We also have maintenance mode feedback in the SAM, which is indeed dominant at low redshift, and it's important for keeping the hot halo gas, keep it hot, prevent it from cooling back into the galaxy and forming stars. But sometimes this maintenance mode can fail, and you can also have mergers that bring in gas, which leads to what we call the third paradigm, rejuvenation. In the SAM, rejuvenation star formation histories are subdominant. And also in the SAM, the upward excursion, many orders of magnitude from quiescence back onto the main sequence is lightning fast compared to the subsequent requenching or fading phase. But I am curious about the realistic distribution, if there's like a realistic distribution of timescales for rejuvenation, if this lightning fast upward transition is actually realistic. Last paradigm is interesting. We call it gentle quenching, and in the SAM, this occurs when the baryonic mass accretion rate of a given halo is lower than its star formation rate, which leads to star formation histories that decline with a much steeper slope than you would expect for star-forming galaxies that live in more average halos with average gas or baryonic mass accretion rates. An interesting thing is whether this is applicable to galaxies like M31 and the Milky Way, where we know that from observations that they've been quenching slowly for several gigayears. That is to be determined. So we have hundreds of these tracks. So what we can do is we can look at studies in a statistical sense. So what we can do is at low redshift in the models, we know galaxies are classified as star-forming, transition, or quiescent. So we can go back in time to redshift 3 and count up how long have they spent in the star-forming main sequence, how long have they spent in the transition region and as quiescent. And the key takeaway point here, I won't go into the details of the plot and the different things, but the key takeaway point here is that in the SAM, there's a significant population of galaxies that have been in the transition region for several gigayears. And some of them reach quiescence at very late times, redshift 0. They take forever to become quiescent, or they may never become quiescent by redshift 0. One thing we can do, we did, is to ask whether this new state-of-the-art implementation of momentum-driven agent feedback and Ina Choi's hydrodynamical simulations helps lower this transition region occupation timescale. And indeed, we do the exact same analysis on the histories, and we find that it does tend to lower the median transition region occupation timescale, but it's not clear to me whether it can fully explain or solve this issue of too many slow quenchers in the SAM. So the general takeaway point here is that the transition population in the observations and in the models are a powerful way to probe the physics of quenching that's implemented in these simulations. And based on the papers that I've read from other simulations, like Illustrious, for example, or Eagle, they also, especially Eagle, they quote classical Green Valley occupation timescales of 2 to 3 gigayears, again, the median. So what I think is interesting to do in the future is to take the observations. We have observed star-forming transition quiescent fractions, the solid lines here, and to compare those to different simulations, perhaps with different types of feedback implemented. The main thing that stands out in the SAM is that at higher redshift especially, there's a significant lack of quiescent galaxies. And again, I think this is probably going to be an issue in other simulations as well, based on what I've seen for their low redshift galaxies. So in the future, it'll be interesting to not just compare, for example, the stellar mass functions, whether the stellar mass functions agree, for the main sequence and quiescent populations between models and observations, but also to further decompose the quiescent mass function, say, based on some measure of the degree of quiescence, as Eric Bell might call it, and see is there good agreement as a function of redshift, and what does that tell us about the relative prominence of gentle versus violent quenching, the evolution of quenching timescales, things like that. So before I move on to my last plot, or last takeaway point, I want to show my favorite plot, which is also from the SAM. And so the SAM seems to predict that transition galaxies also exhibit intermediate properties in terms of relative to the other two subpopulations. So there's mean stellar ages, there's cold gas fractions, there's supermassive black hole masses, which is interesting to me, and also in terms of environment, we have halo masses. So my last key takeaway point here for future work that we're working on now is what you really want to know is the redshift evolution of the gentle quenching paradigm versus the violent quenching paradigm, and one way to do that is to look at the structural evolutionary histories of these galaxies and try to figure out how do these morphological change timescales compare to transition timescales, and to try to connect this up with some observational work that's been done at low redshift which seems to suggest a simple picture where, you know, disky galaxies transition very slowly and bulge-dominated galaxies transition very fast, but I think that might be too simple, especially if morphological change can accompany quenching very slowly, so a galaxy can grow a bulge at the same rate maybe as it quenches. So it's not clear. And that's it. Thank you.
Well, we'll allow one question here.
Very simple one. Using the SAMs that you were showing, would the Milky Way qualify as transition, and if so, would it be considered a long-term one?
I think it would be a long-term one, and I think it would be transitioned by redshift 0. Eric Bell thinks no.
A lot of people do consider the Milky Way as low in specific star formation rate, but according to the plots I've made, it's pretty close to the star forming main sequence.
Okay.
So, I mean, but this is not a consensus view. There's quite a bit of dispersion in the literature on star formation rates for the Milky Way.
Thank you very much. Thank you, Viraj. Okay. Thanking everyone.